In number theory, the specialty additive number theory studies subsets of integers and their behavior under addition. Additive number theory has close ties to combinatorial number theory and the geometry of numbers. Two principal objects of study are the sum set of two subsets A and B of elements from an abelian group G, and the H-fold sum set of A. There are two main subdivisions listed below. Additive number theory. The first is principally devoted to consideration of direct problems over the integers, that is, determining the structure of Ha from the structure of A. For example, determining which elements can be represented as a sum from Ha, where A is a fixed subset. Two classical problems of this type are the Goldbach conjecture and Waring's problem. Many of these problems are studied using the tools from the Hardy-Littlewood circle method and from sieve methods. For example, Vinogradov proved that every sufficiently large odd number is the sum of 3 primes, and so every sufficiently large even integer is the sum of 4 primes. Hilbert proved that, for every integer k greater than 1, every non-negative integer is the sum of a bounded number of kth powers. In general, a set A of non-negative integers is called a basis of order H if Ha contains all positive integers, and it is called an asymptotic basis if Ha contains all sufficiently large integers. Much current research in this area concerns properties of general asymptotic bases of finite order. For example, a set A is called a minimal asymptotic basis of order H if A is an asymptotic basis of order H, but no proper subset of A is an asymptotic basis if order H. It has been proved that minimal asymptotic bases of order H exist for all H, and that there also exist asymptotic bases of order H that contain no minimal asymptotic bases of order H. Another question to be considered is how small can the number of representations of n as a sum of H elements in an asymptotic basis can be. This is the content of the Erdos-Turan conjecture on additive bases. Additive combinatorics. The second is principally devoted to consideration of inverse problems, often over more general groups than just the integers, that is, given some information about the sum set A plus B, the aim is find information about the structure of the individual sets A and B. Unlike problems related to classical bases, as described above, this sub-area often deals with finite subsets rather than infinite ones. A typical question is what is the structure of a pair of subsets whose sum set has small cardinality? In the case of the integers, the classical Freimann's theorem provides a potent partial answer to this question in terms of multidimensional arithmetic progressions. Another typical problem is simply to find a lower bound for A plus B in terms of A and B. Examples of this type include the Erdos-Heilbronn conjecture and the Cauchy-Davenport theorem. The methods used for tackling such questions draw from across the spectrum of mathematics, including combinatorics, ergodic theory, analysis, graph theory, group theory, and linear algebraic and polynomial methods.